In this lesson, we'll take a look at approximating the slope of a tangent, which is an instantaneous rate of change using the slope of a secant, or reading the slope of the tangent directly from the graph. Now, the slope of a tangent line is called an instantaneous rate of change because it represents how fast something is changing at a single point or at a point in time, not between two different points or two different points in time. And so in a previous note, we talked about how this graph would change from the point P to the point Q, and that was an average rate of change over a distance delta x, a run delta x. And we can find that rate using the slope formula. Now, instead in this lesson, we're talking about how the graph is changing at a single point, how it's changing at just the point Q, how quickly y changes with respect to changes in x. And so notice that the tangent only touches the curve at a single point Q, and so there's not two different points in the curve that we can use the slope calculation to find the slope of it. Now, one technique here is to take that point P and move it closer to Q along the curve, and what I mean by that is this. If I were to take point P and move it to here and draw a new secant line, there's my yellow new secant line, the slope of that new secant line is closer to the slope of the tangent line than the original secant line, with going through point P here and Q. And that's because I've taken that point P and moved it closer to Q. If I take that point and move it even closer, for example up here, and draw a new secant line, notice my point P is actually quite close to Q now, and so this red secant line looks even more like the tangent line than either of the first two. And so of the three secant lines, the red one, the last one I drew, its slope would be the closest to the actual tangent line slope of the three of them. And that's because its point P is the closest to Q along the curve. And I'm going to show you that in a Geometry Sketchpad diagram as well. And in this diagram, here's the parabola, and my tangent point is at point P. And we can read actually from the graph, and I've drawn a right triangle here. The rise is 2, the run is 1. 2 divided by 1 is 2. So the tangent slope is certainly 2 there. And I've drawn a secant. Here's my Q point. That's my movable point. I'm going to move that down along the curve here. Right now, we can read from the graph that the rise is 8, and actually there's the rise right there. And the run is 2 blocks along here. PR is the run is 2, and 8 divided by 2 is 4. So the slope of my secant is 4. Now if I take that point Q and move it down along the curve, notice the secant line is looking more and more like the tangent line. And if I take that point Q and move it even more, notice that the secant is looking a lot like the tangent, and notice that my slope is getting closer and closer to the tangent line slope. And if I take that point Q and make it really, really close, it's so close now that the secant looks almost identical to the tangent. And notice that my slope 2.03 is actually pretty close to the real tangent line slope. So that's what I mean by moving the 2 points on the secant so close together that the secant slope is almost the same as the tangent line slope. And so back to the PowerPoint here. So we say that as P approaches Q, as the two secant points get closer and closer to one another, the slope of the secant PQ approaches the slope of the tangent line. And so the closer that P gets to Q, the closer those 2 points are, the better the approximation. Okay, one example on the second page here, we have an object free falling. Its distance obeys the formula. Distance is 4.9 times the time squared. And in a previous note, we generated this table by putting times from 0 to 5 in place of t, and there's the distances. And so a couple of average rates of change between points. Now we're trying to find the instantaneous velocity at 3 seconds. And so previously we found the average rate of change from 2 to 3 seconds. And so we went and subtracted 19.6 and 44.1. And that's the calculation here, over a change in time from 2 to 3 seconds, which is 1 second. And so the average rate of change, or average velocity from the second to the third second, we got to be 24.5 meters per second, which is the slope of this secant. From 3 to 4, this is the calculation here, From 3 to 4, we subtracted these distances and these times, and that slope is 34.3 meters per second, or that average rate of change from the third to the 4th second is 34.3. Now what we want to do is, and I just drew a tangent line, is actually find the real tangent line slope at Q at 3 seconds. And so notice that that tangent is steeper than the first secant, so the velocity we're looking for is bigger than 24.5, but the tangent line slope is not as steep as the from 3 to 4 average rate of change here. And so the actual instantaneous velocity, 3 seconds, must be smaller than 34.3. So it's some number between 24.5 and 34.3. Now one thing we could do is we could read from the graph the tangent line's slope. So you could take a couple of points in the graph. So for example, that's a point, and I'll take this point up here as well. And then we could read from the graph that there's a change in time of 3.5 seconds. And this would be, of course, our rise. The change in displacement is 100 meters. And so we could use those, and the slope here, or rate, is change in displacement over change in time. And so we're dividing 100, that's the change in displacement, by the change in time of 3.5 seconds. And so it looks like the slope of that tangent line is about 28.6 meters per second. And so that's a pretty good approximation for the instantaneous velocity at 3 seconds. The accuracy of that depends on how well you can draw the tangent line. Okay, so if you draw it a little bit off, then however much you draw it off is going to be how much your calculation will be away from the real instantaneous velocity at 3. But that's a pretty good approximation. Another thing that you can do is you could take more times besides the ones that are in the table here. For example, I'm talking about the instantaneous velocity at 3 seconds. These calculations were over a period of time of 1 second. So if you took a time close to 3 seconds, like 3.1, and filled the 3.1 in place of time, 3.1 squared times 4.9 is 47.1. And so what I'm going to do now is use, again, the rate is change in distance over change in time, from 3 to 3.1 seconds. And so my change in distance, or displacement, is the difference between the 44.1 and the 47.1. So there's my change in displacement there. And the change in time is from just 3 to 3.1 seconds. So there's my change in time there. And so that gives me an average rate of change over that fairly short time interval of 30 meters per second. And that's a pretty good approximation because the change in time is only 1/10 of a second. And so it's a pretty short time interval. So that point S would actually be pretty close to Q here in the graph. Now I could get even closer if I wanted to. I could take a time of, let's say, 3.01 seconds, only 1/100th of a second bigger than 3. And so if I fill 3.01 in place of time here, 3.01 squared times 4.9 is a distance of 44.39 meters fallen. And so I'll find, using the slope calculation again, the slope between this point and this point. And so the change in distances are 44.39 minus the 44.1. And the change in time is 3.01 minus the 3. So there's the change in time. And that will give me a velocity of 29 meters per second, so even closer to this one. Notice that this one's closer to this one. This must be pretty close to the real one, because I took a shorter time interval. This is over a 1/100th of a second. This is 1/10 of a second. And so that's a pretty good approximation because I took my change in time to be very small. And so we could say with a fair bit of confidence that the instantaneous velocity at 3 seconds is about 29 meters per second. And that's the end of the lesson.